Hello, and welcome to Minerals, Rocks, and Fossil Talks. I'm your geology teacher, Jen, and I'm glad that we get to still do this on TikTok, because you guys are fantastic. It's time for another Monday Musing. Today we're going to learn about the Ordovician Meteor event, which was a dramatic increase in the rate at which L-chondrite meteorites fell to Earth about 467.5 million years ago, give or take a few. So, what the heck do I mean by an L-chondrite meteorite? Glad you asked. Chondrites are stony meteorites that have not been modified by either melting or differentiation of the parent body. L-chondrites are ordinary chondrites, meaning they are some of the most common meteorites found on Earth. About 80% of all meteorites are ordinary chondrites. There are three types of ordinary chondrites: H, L, and L. This comes from the iron metal content. H is high in iron, L is mostly iron silicates with some less than 10% iron, and LL has almost no iron. During the Middle Ordovician, dozens of L-chondrites hit about 30 degrees north of the equator, right where Laurentia and Baltica were. According to a 2019 study, this temporary increase in the impact rate could have been caused by the destruction of the L-chondrite parent body that was about 153 kilometers or 93 miles in diameter and orbited in the asteroid belt between Mars and Jupiter. However, a 2004 study found that all of the 21 studied craters from this event were at the time within 30 degrees of the equator. Impactors directly from the asteroid belt would be expected to produce a random distribution of craters. So this suggests that the event may have been caused by an asteroid that passed within Earth's Roche limit and broke up into a ring system, material from which then deorbited and formed the craters. So here's how that would play out. So in this depiction here, this is basically our planet, and this will be the asteroid or satellite or whatever it happened to be at the time, and this white line is our Roche limit. So basically, when it's not within that limit, it's round, it does its thing, and then our gravity pulls it in, it starts kind of yanking it that way towards us, and then it starts to tear it apart. As it gets torn apart, it gets kind of yanked into our orbit and breaks into pieces and forms a ring. It was speculated at one point that this event contributed to the Great Ordovician biodiversification event, possibly even started it, but many also question that and say it was just a separate event altogether. It is also speculated that it contributed to the Hernantian or End-Ordovician glaciation. What's the evidence for that? Well, the breakup of the L-chondrite parent body would have caused a rain of extraterrestrial material onto the Earth and increased stratospheric dust by 3 or 4 orders of magnitude, and may have triggered the Ice Age by reflecting sunlight back into space. Kind of like Venus's atmosphere, which is so stinking thick. That's why we can see it pretty much every night, that it's in the right spot. A study from last year suggests that rather than a complete breakup or outright impact, the L-chondrite parent body may have had a near-miss encounter with Earth, causing a part of it to break off from Earth's gravitational pull. This debris may have formed a planetary ring, and downfalling debris from this ring may have shaded Earth from the sun's rays and triggered significant cooling. Evidence for this comes from the fact that craters dating from the Ordovician meteor event appear to cluster in a distinctive band around the Earth instead of being randomly scattered, which may have come from debris falling to Earth from the ring. And this ring may have lasted for nearly 40 million years. Either way, there was some sort of meteor event during the Middle Ordovician, and it may or may not have had a big impact on life at the time. Tune in tomorrow for a quiz on meteorites, and I will fossilize you later.